Anyways, what is the most important thing in calculus? The most important construct in all of calculus. Let's go. Come on. We're 2 lectures away from the end of calculus 1, and everyone here, good. Ayana, thank you. Ayana, thank you. We got it on the first try. Did you cheat? Did you look up the answer, Ayana? Did you look it up? It's okay if you cheated for this one. It's okay. The limit. Good. Nope. She knew it. The limit is the most important thing in all of calculus. Everything is based on it. It's what separates pre-calculus from calculus. Now, we got 2 things that come from limits, and they're tied for the second most important thing in calculus. What are they? Derivative is one of them. Antiderivative? No, antiderivatives are just derivatives. They're the same thing. Integral. So, first of all, why do these come from limits? Let's remind ourselves. Why do they come from limits? Well, the derivative is a limit, right? F prime of x is defined as what? It's the limit as h approaches 0. F of x plus h minus f of x all over h, right? The derivative is defined as a limit. And the integral is also defined as a limit, right? We talked about this last lecture. The integral of f on the interval ab. I'll just write it's the limit as n goes to infinity of the associated Riemann sums, right? That's what we talked about last time. So integrals and derivatives are both defined in terms of limits. What are their interpretations? Derivative, what is your primary interpretation of a derivative? Why do we care about that? What does it tell us generally? Slope of the tangent line. Okay, good. So it gives us a slope of tangent line. All right, that is our primary interpretation of the derivative. Right, and then we can use that for all sorts of applications. Like we saw related rates, we saw optimization, we saw graphing, we saw finding maxes and mins, right? We saw a whole bunch of applications of that concept. What is the interpretation of the integral? Area under a function, area under a graph. Okay, so area under graph. Okay, so is there a link between these 2 things? Yes. So up until now, these 2 things have not been, up until now, these 2 things should have been thought of. They're just separate quantities. I mean, derivatives and integrals have nothing to do with each other, right? I mean, one is a slope, one is an area. And now we're going to talk about, is there a link between them? And that is the fundamental theorem of calculus. So that's what today's topic is. Fundamental theorem of calculus tells us that derivatives and integrals are actually not so different after all. Okay, now traditionally the fundamental theorem is just one theorem. It's one theorem, but traditionally introductory textbooks typically split them up into 2 parts. Some books call part one. That sometimes they call it part 1, part 2. Sometimes whatever. I forget what your textbook calls them. So I'm gonna call whatever I call part 1 and part 2. That's what I'm calling them. It doesn't really matter. They're the same theorem anyway. Actually, yeah, whatever. So this is fundamental theorem part 1. Okay, so suppose f is continuous. On AB. And suppose big F is an antiderivative. So that's where derivatives are going to come into play. They're going to come in through antiderivatives. So if you have an antiderivative of a function, antiderivative of a continuous function, you can calculate an integral. You don't need to use geometry. You don't need to use Riemann sums. You can calculate it by computing the antiderivative and subtracting the 2 numbers, f of b minus f of a. Now, unfortunately, we actually won't have an opportunity to prove this. It's kind of a very nice proof, and it really does show you the why derivatives come into play with area functions. Unfortunately, we haven't covered what's called the mean value theorem, and you need that to actually prove this. But it is essentially an application of the mean value theorem. So if you are curious, you can read those optional notes. Okay, so first of all, I just want to kind of keep on emphasizing the difference between an antiderivative and an integral. Again, I know a lot of you have taken calculus and you get these things confused. You think integrals are antiderivatives. They are not. All right, antiderivatives can be used to calculate integrals, but they're not the same thing. So I just want to kind of recall some notation here. So if I have an integral sign with numbers on it, right, a to b, versus an integral sign without numbers on it, right, just to remind you what these things mean. Or the thing on the left, that is called the integral of f. On the interval AB, right? It is the area under a graph. And the important thing here to note is this is a number. It's not a function, right? This is a number because it's supposed to be the area of a certain region, or the net area, right? Because f might dip below the x-axis. And if I don't have numbers on the integral sign, that's an antiderivative, right? This is the most general antiderivative of f, right? And in particular, this is not a number, it's a whole family of functions, right? So these two things, they're not even the same type of object. One is a function, one is a number. So please make sure you understand the difference between them. Okay. Now, there's part 2 of the fundamental theorem of calculus. Okay, so I'm going to write this down. So FTC part 1 kind of tells us what to do with antiderivatives. So FTC part 1 tells us if we already have an antiderivative, we can use that to calculate an integral, right? But this kind of begs 2 questions. So one question. Does every function actually have an antiderivative? So in other words, if I just write down any old function, is every function you can give me the derivative of some other function? This is beyond the scope of the course. The answer is no. Not every function you give me is actually the derivative of some other function. It turns out that actually derivatives are pretty rigid. They have to have certain properties. Like, for instance, if something really is the derivative of something else, one property it has to have is called the intermediate value property. If you give me any, it doesn't skip any values, for instance. Derivatives can also not have jump discontinuities. They cannot have, they really can't have asymptotes either, technically speaking, but we gotta get away with that in other ways. But yeah, not every function is actually a derivative, but all continuous functions are. So that's one thing to keep in mind. Not everything even has an antiderivative. So if you're talking about the area underneath a graph of a general function, fundamental theorem calculus actually won't help you find those integrals. And you might think, oh, this is beyond the scope of the course, doesn't really show up. It actually does show up in quite a lot of applications, these types of functions. So. And there's some other question So if the antiderivative exists, so suppose I do have a continuous function, or I do have some function whose antiderivative exists. How do you actually find it? How do you find, I'm going to say, a useful formula for it? Because I'm going to write down a formula for an antiderivative in just a second, but it's actually not going to be very useful. And this is actually a much deeper question. And it turns out this is very difficult to answer. And the first half, or the first third of Calculus 2 shows you some ways to do this. So this second question is actually another reason why the fundamental theorem of calculus is very useful theoretically, and why it's very useful, say, for doing all the examples we give you are contrived in such a way that fundamental theorem of calculus can be used. But in practice, a lot of applications, fundamental theorem of calculus is completely useless. You would do things by a computer, or you would estimate things, or these functions don't even have antiderivatives in terms of elementary functions. So it's nice that sometimes we can find antiderivatives, but honestly, it's not really that important. So fundamental theorem of calculus part 2 kind of answers the question. It tells you that all continuous functions have an antiderivative, and it does give you a formula for such an antiderivative, but it's not very useful. So what do I mean by that? So we'll see in a second why it's actually not very useful. Essentially, what fundamental theorem part 2 tells you is if a function has an antiderivative, you can use the integral to define the antiderivative, which really gives you, which is really not useful for finding the integrals, but it is nice theoretically that the integrals also serve as antiderivatives. So suppose f is continuous on AB. Let x be some number in AB, and define a of x. So this is an interesting function. So look at this function. So this function, notice that the variable is in the upper limit of integration. In other words, the variable of the function is the rightmost endpoint of our interval. So in other words, the function a of x, so f is fixed. The function f is fixed. Here's f. The number a is also fixed. So here's a. All right. And here's b. X is just some number in between here. So here's x. Now, what is a of x? A of x is the area underneath the graph up until that value of x, right? And you can imagine, so a of x actually gives the area underneath the graph. It's a function that gives the area underneath the graph, where the variable is this rightmost endpoint, right? I can also move it, say, over here, and there's a different value of a of x. So we're defining a function in terms of area. So what does fundamental theorem of calculus tell us? Fundamental theorem of calculus tells us that the derivative of this area function is f of x. In other words, the derivative of a function defined via an integral like this is just the function f. So this is a derivative rule. Actually, fundamental theorem of calculus tells you how to differentiate integrals. Fundamental theorem of calculus part 2 tells you a few things nicely theoretically. It's not a very useful theorem in terms of finding antiderivatives, but it tells you a few things. First of all, it tells you that all continuous functions have antiderivatives. It tells you that integrals can be used to define antiderivatives. So in other words, it doesn't give you a formula for the antiderivative, but it does tell you, for instance, if you had a way of approximating this number on the right-hand side, say using a computer, you can find an antiderivative of the function at that point. So there actually are schemes for computing this thing on the right using a computer for many different values of x. And now you have kind of an antiderivative, maybe say for 100 values of x. So that's kind of useful. It also tells you how to differentiate an integral, right? It essentially tells you that the derivative and the integral are kind of inverse operations of each other. You know, they undo each other. Okay. Right, because this tells you derivative of an integral is the original function. And if you want to look back at part 1, this is essentially saying the integral of a derivative is equal to the original function, you know. So both parts are actually saying the same thing, essentially. Anyways, so that's the theoretical background for this section. Whoops.